welcome back. We will continue our discussion on energy balance with chemical reactions, which we just started in the previous class. This class now knows what is heat of formation, and therefore, that gives us a formalism for calculating the heat of reaction. So, we all know about heat of reactions, we had all known about it for a long time from our school days about endothermic and exothermic reactions. And we also realize that in exothermic reactions, the total enthalpy of the products, right, is actually lower than that of the reactants, and therefore, some energy gets released, right. But how do you sort of quantify the total enthalpy of the products? So, the total enthalpy of the products or the change in the enthalpy of the reactants and products can be quantified in terms of heat of reaction. And what about the individual components? So, that is related to what is known as the heat of formation. So, we have talked about heat of formation, and we have also learnt about the formation reaction, and we learned something very interesting, that a formation reaction can be a true reaction or it can be a fake reaction also. So, therefore, when we talk about, let us say, the formation reaction of carbon dioxide, there is absolutely no problem, because formation reaction of carbon dioxide, for example, so formation reaction, you must mention the states, because they must, all the products or the reactants must be in their natural state. So, this is a true formation reaction, there is absolutely no problem. But let us say when we talk about carbon monoxide, we can certainly write the formation reaction, and this is the formation reaction we have. Right. So, there is no problem in writing the formation reaction. So, C plus half O2. So, you take stoichiometrically half amount of oxygen in principle, and you should get carbon monoxide, but that does not happen. What happens is, we had discussed in the previous class that if you have less amount of oxygen than the stoichiometric requirement of carbon, what will happen is some part or 50% of the carbon will get converted to carbon dioxide, right, and remaining 50% of the carbon will remain unreacted. But then how do you calculate the heat of formation of something like carbon monoxide, because or any product. So, the question essentially emerges is how essentially do you calculate the heat of formation of all compounds which have fake formation reaction, right. So, this is the question we were looking into, and then we realized that though this reaction is fake, oxidation of carbon dioxide, carbon monoxide into carbon dioxide is possible, is highly possible. This is a reaction which is possible, and then the moment a reaction is possible, using some instrument, maybe a calorimeter, you can actually measure the heat or the thermal effects associated with it, or the change of energy associated with a particular reaction. So, here is the situation. We have the, what we have is the, we know the formation reaction of CO2, or we know this delta HF0 for CO2 is known to us, and for this, so this is a fake reaction, this is not available. So, let us strike it off. So, this reaction is a fake reaction. So, no data is available on this, right. This is a fake reaction, but nonetheless, though it is a fake reaction, this is the formation reaction, and the heat of reaction for this particular reaction is known. So, here comes a very important concept of what is known as the Hess law, which essentially has two basic meaning. So, I will come to it, and it is very simple actually. So, this is known, and this turns out to be minus 282.99 kilojoule per gram mole of carbon monoxide, and this value is heat of formation of carbon dioxide, or the heat of reaction of this particular reaction is minus 393.51 kilojoule per gram mole of carbon. Okay. So, now according to the Hess law, which is a very important formalism, the heat of formation, I am writing it down for the benefit of all, the heat of formation of carbon monoxide, and the moment we say heat of formation of carbon monoxide, it means that from its constituents in their standard state, etc., etc. So, the heat of formation of carbon monoxide is same as number 1, formation of CO2 from its elemental elements or elements in their standard form, followed by number 2, decomposition of CO2 into carbon monoxide and oxygen. So, what exactly does it mean? The inner implication of this particular reaction, this statement is that if this is the heat of reaction of the forward reaction, the heat of reaction of the backward reaction will be exactly the same, but the magnitude will be negative of whatever is the heat of reaction for the forward reaction. Please take a minute to convince yourself. So, for this particular reaction, the heat of reaction will be simply 282.99 kilojoule per gram mole of carbon monoxide. So, two things. So, one is the Hess law. So, now let us try to find out what Hess law says. So, what Hess law says is as follows. I am coming back to that reversibility thing. So, Hess law, the consequence of Hess law is the thermal effect associated with this reaction is same as followed by dissociation of carbon dioxide into carbon monoxide and oxygen. This is the implication of Hess law. This is what Hess law says. So, this series of reaction, this reaction series will have same thermal effects as that of the formation reaction of CO, right. So, this is what Hess law says, and the other thing that we have used is, so we should actually, I mean let me write it once again, or maybe we can avoid this by sorry. So, this is what it says, effects formation reaction. This reaction series will have same thermal effects as the formation reaction of CO. Sorry for the little jumbled up writing. There is a reason why I vacated this place. Some of you can probably start guessing it already. In fact, this is again a problem I have made. I should have been more careful. Okay. Whatever. So, the other thing is that this reaction, which is the heat of formation of carbon dioxide, gaseous carbon dioxide, the energy is associated is minus 393.51 kilojoule per gram mole, and this one, the heat of reaction now for the backward reaction is 282.99 kilojoule per gram mole. So, this is the other important thing, because here we have talked about this particular reaction, this oxidation reaction of carbon monoxide has a heat of reaction of minus 282.99. So, theoretically if there is a dissociation, there is another important question whether this dissociation actually happens or not, and it is not that easy to happen. Carbon dioxide is a very, very stable compound and it does not dissociate, but so therefore, this can again be a fake reaction, but what we are considering that if the thermal effect or the heat of reaction for the forward reaction is known to us, then the heat of reaction of the reverse reaction or the backward reaction will be exactly its opposite. The number or the value will be same and the sign will simply change. So, if that be the case, now what we do, we treat these two chemical reactions simply like two algebraic equations. So, just add the left side and the right side, and what you get is carbon plus oxygen plus CO2, and on the right hand side you have CO2 plus carbon monoxide plus half oxygen. And you can also add these two. So, the net heat of reaction according to Hess law is going to be minus 393.51 kilojoule per gram mole plus 282.99 kilojoule per gram mole, and is equal to it is minus 110 or something like that, minus 110.52 kilojoule per gram mole, right. And if you now look into this equations, what you have obtained after adding, you see that there is carbon dioxide on both sides. So, it gets cancelled out, and here you have 1 O2 and here you have half O2. So, essentially what you have on the left hand side after you remove this is carbon plus half O2 leading to carbon monoxide in gaseous form. So, this is what is Hess law, and this is a very, very powerful technique. So, what you have seen after a little bit of hassle, not exactly hassle, little bit of understanding, right, we have actually very nicely utilized the concept of Hess law in the sense that so essentially the formation of carbon monoxide from its constituent elements, the energy associated with the formation of carbon monoxide from its constituent elements is essentially the same as obtaining carbon dioxide, and then if you consider that carbon dioxide gets dissociated into carbon monoxide and oxygen. And in the process you have just taken one more, we learnt another important thing, that whether a reaction happens or not, chemically happens or not, that is a different question, but what you can write is that if you know the heat of reaction of the forward reaction, the heat of reaction of the backward reaction is exactly its opposite value, the negative of the same value. And if you write those, and all you have to do is essentially according to Hess law, you write these two equations and then you simply add them up over here as if these two are like algebraic equations here, that is a rule of thumb I am telling you. do not say all these things, but this is how you proceed, right. And so, essentially after that you also add up the heat of reactions and do a cancellation of the similar terms and do the basic algebra over here, like you have 1 O2 on the left hand side and half O2 on the right hand side. So, it is essentially it is as similar to having net half O2 on the left hand side. So, what you get is carbon plus half O2 leading to carbon monoxide, and therefore, you can calculate the heat of reaction heat of formation of carbon monoxide using Hess law. Using Hess law and some feasible reactions or actual reactions that take place for a particular compound which may have a fake formation reaction, right. So, this is the important concept what I thought I should teach you. And then once the heat of formation is known, the heat of calculating so it comes like this. Once the heat of formation of all reactants and products are known, you can calculate the heat of reaction. That is easy, right. For example, we have this particular reaction taking place, C6H6G plus 3H2G leading to C6H12G, right. And what is known is heat of formation of C6H6G is 82.927 kilojoule per gram mole, and heat of formation for C6H12 is minus 123.10 kilojoule per gram mole, right. So, if I now ask you to calculate the heat of reaction, so can you calculate the heat of reaction? The answer is everybody will say yeah, we can calculate, because see this is an element and therefore, its heat of formation is 0, but here comes the real rider, your real understanding. Your answer should be yes, we can calculate the heat of reaction, but only we can calculate this value only at 25 degree centigrade and 1 atmospheric pressure, or in other words, if this reaction proceeds at 25 degree centigrade and 1 atmospheric pressure, then only we can calculate the heat of reaction values. Why? Because these are all standard heat of formation data. So, whatever is provided, though we loosely say this is heat of formation, this is actually standard heat of formation. This is standard heat of formation data, right. So, this standard heat of formation is valid, or the so called heat of formation data you have is only at 25 degree centigrade and 1 atmospheric pressure. So, therefore, if I ask you, and if somebody is very careful about pedagogy, and if I say can you calculate the heat of reaction, I have not mentioned that I am specifying the temperature and pressure. So, please do not fall into the trap that you can with this data calculate if this reaction, let us say, is happening at 40 degrees at let us say 100 degree centigrade and 1 atmosphere or 5 atmospheric pressure, you cannot calculate. So, let us say now essentially you have, so we can calculate the heat of reaction for this particular equation, and standard heat of reaction at under standard condition, which will turn out to be the product, the heat of formation of the product minus the heat of formation of the reactants, plus 0 comes for hydrogen and therefore, this is equal to minus 206.0 kilojoule per gram mole. Okay. So, this you can calculate. Now, think of a situation. There are several very small issues associated with it, which I can explain very nicely. We can develop a very nice understanding. So, one of them can be, let us say this reaction goes to 70% completion. So, what does it mean? 70% of the reactants have reacted to form some product. So, what is the final product? Had the reaction gone to complete 100% completion, then the final product stream would have contained only C6H12. But now it says that the reaction has progressed only up to 70%, let us say. So, what will be the composition of the final product? Final product will be 70% will be C6H12, right, and remaining part. So, 30% here does not mean anything, because this is a molar fraction or whatever, but the final product will comprise of C6H12. You understand it very well, because you have learnt about incomplete combustion in the other part. So, it will contain and some hydrogen also. This will be the product. That is perfectly fine, that the number of moles you can find out considering a basis from your mass balance, understanding of your mass balance, that is not a problem. But the question is, if the reaction has gone up to the level of 70%, what is the amount of heat associated with the reaction? And it is very easy, you calculate. So, if the reaction has taken place at 1 atmospheric pressure and 25 degree centigrade, and you know the percentage conversion or whatever, it is very easy. Whatever is the heat of reaction you get, you simply multiply it with the eta, right, for an incomplete reaction. So, if eta is the percentage of the reaction, then the total heat, actual heat. So, associated with the reaction is eta into whatever is the standard heat of reaction, and in this particular case it is going to be 70, so that is 0.7 into 206. That is very simple. Now, I have a question. So, let us say you have this reactor, you have a reactor, and let us say two reactants. This can be elements or compounds. Let us say these are compounds. Let A and B be C, D all be compounds, or it can, some can be reactants, some can be elements also, right. What is the only difference if you have a compound versus an element? If you have compounds, you will have non-zero heat of formation values. If you have elements, the heat of formation values will be 0, right. So, they can be compounds or elements or whatever, and let us say I say that this one enters at temperature T1. For the simplicity, let us assume everything is at 1 atmospheric pressure. The B enters at a temperature T2, and it is not very wise to write that C and D to just to make the problem more complicated. It is not very logical to write that C and D lives at two different temperatures, because after all they are coming out as the reactor product, and probably they will have the same temperature as that of the reactor. So, let us say C and D. So, I hope all of you understood what I meant, that in principle the two raw materials or the feeds can enter the system at two different temperatures, but the products typically, even if there are two products which are, let us say one is a gaseous product and one is a liquid product which live separately, it is very difficult to imagine a situation that the two products live at two different temperatures. Probably they will live at the same temperature. And what we write is T1, T2, T3 are none of them are equal to 25 degrees centigrade, let us say they are all above 25 degrees centigrade. So, what exactly do you do? How do you calculate the heat change associated with it? So, let us say you have been told that this is a so why do you need this data, for example? What exactly are you going to do with the heat of reaction data other than just calculating and getting some marks in this course? So, it is like if you have an exothermic reaction, you know that heat will get generated, right. So, if heat gets generated, what will progressively happen? The reactor temperature will go up. Now, which you do not want, you may want, there are many effects which you will learn in your reaction kinetics later. The reaction may become slower with time, or if there is continuous generation of heat, the reactor becomes too hot and there can be potential material failure. If the reactor becomes hot, there are issues associated with insulation, some rubber lining may go bad, and all these things can happen, right. So, it is generally lot of reactors actually work under isothermal conditions. So, you have to maintain the temperature. So, how does this calculation help? So, based on this calculation, now from the heat of reaction data, you now know how much amount of heat is going to be generated, and therefore, accordingly around the reactor you might actually having a cooling jacket, right, where you might enter water, let us say at room temperature, and you modulate the flow of water in such a way that let us say water leaves at 45 degrees centigrade or something like that, right. So, how does your heat of reaction data help? Heat of reaction data helps in a way that you now know how much is going to be the water flow rate. Also, please do not think that you would like to cool down a reactor and therefore, you will take water at 0 degree centigrade. Industrially, it does not happen like that. Nobody at the site of the plant is going to run an additional chiller plant for producing cooling water, right, which is just an utility, which is not even participating in any reaction. Nobody is going to cool it down to 0 degree centigrade or 5 degree centigrade, so that you know a lot of things. Okay, so why do we take water liquid? Let us take ice at 0 degree centigrade, then we can harvest the not only the latent heat, not the sensible heat only. Nobody is going to give you all that. So, you will be given water, right, at whatever is the temperature. So, these are actually design problems that if you have a plant where there is seasonal fluctuation of temperature, which is very common in a country like India, how essentially do you handle your water supply system? And then again I have written an outlet temperature of 45 degrees centigrade, right. So, why 45 degrees centigrade? Why not use less amount of water and go all the way up to let us say 100 degrees centigrade? Because you have to consider that if you release water at 100 degrees centigrade, that can itself be a hazard for the operators or the people around. So, everything has some limits. I mean, this is not a design class, so I cannot go into all the detail. So, this is the utility of the heat of reaction. So, now we are running out of time. So, what exactly do? We essentially have reactants entering at different temperatures, product leaving at different temperature, but we know we can calculate the heat of reaction data only at 25 degrees centigrade. So, what we will consider is as if whatever is the temperature of A, it is brought down from T1 to 25 degrees centigrade, B is brought down, and how do you calculate? You know the mass of this A, you know the Cp values of this A, and then once as if they are down to 25 degrees centigrade, now you can calculate the heat of reaction, and based on that at 25 degrees centigrade and 1 atmospheric pressure. So, you can very well calculate the heat of reaction data, and you get C and D at 25 degrees centigrade, and then if they are living at a higher temperature, you can again consider what is the amount of heat that is required for heating up that temperature, and from there you can calculate. So, it is like sometimes if you have to cross a deep gorge in a hilly road, you might have seen that you do not have a bridge at a very high level. You go down along the first hill, go to the base, there is a bridge which crosses the river, and then you go up again. It is something like that. So, all this initial temperature you first bring it down to 25 degree centigrade, have the reaction out there, and then again heat up to the final temperature. This is how you can do the calculations. So, I will write the mathematical expression associated with this in the next class and get started from here. Thank you very much.